Cool. So we're going to spend a little bit of time diving into the details of 2.1. So starting with the state of Torch compile with Peng, the ecosystem itself, distributed, inference, export, and then finally execute Torch, which is something new from the team. So I will now pass it off to Peng to dive into the details. Thank you.
Good morning, everyone. Oh, here. Yeah, exactly 10 months ago at the same conference, we announced PyTorch 2.0 and a simple API called Torch compile. So I think you guys are wondering, number one, did this thing work? And if the answer is yes, you probably also wonder, what's new here? So state of Torch compile. In a nutshell, it did work. We actually get very healthy signals from the community in terms of adoption. And there are tons of new features in 2.1 in terms of performance and in terms of deployability. So let's first look at the responses from the community. I think yesterday you probably already get a glimpse of it, and just check how many posters have Torch compile or compiler in there. And I think you will get another validation today in today's program. But actually, our mental model of adoption target 3 demographics. So number 1 is the machine learning researcher. Number 2 is vendor or partners. And number 3 are customers with large deployments. So ML researchers are the quickest to try it out. So almost immediately after the announcement, we started to see Twitter feeds on people trying it out and say, oh, 30% improvements, 2x improvement, 3x improvements. And we also tracked the number of distinct GitHub repos that use Torch compile. And here you can see the point where we did the release and how the curve is healthily increasing to the right. We also double-clicked on the repos there, and we saw some heavy hitters like Hugging Face, PyTorch, PyG, and NanoGPT, and the list goes on and on. So the next set of adoption came from vendors because they took some time to actually develop new backends. At the time of announcement at 2.0, we have the NVIDIA GPU backend and CPU backend. And now we are proud to see the lists are growing, and some of our partners will present their integration story in this very conference. When I asked them, what do you like about integrating with Torch compile? They said 3 things. Number 1, the interface. Users don't have to change their code. Number 2, it's a much smaller integration surface. So for example, if you integrate at the inductor level, there are no more than 60 inductor IRs, which can map onto hundreds of ATAN ops. And number 3, again, if you integrate deeper into the stack, actually you can benefit a lot from what inductor already provide, fusion, graph optimization, so you don't have to reinvent the wheels. And in fact, right now, we are very, very confident in promoting Torch compile as the main interface for vendors to integrate their backends over legacy systems like TorchScript or FX. So the last demographic is customers with large-scale production. And these are still work in progress, and naturally so, because it takes maturity to enable Torch compile in a complex system. But we're proud to say that we have seen very positive signals that Torch compile indeed can improve performance on complex models, although the experience is still not yet completely out of the box. And I want to say that actually the targeting this segment is actually the driving force behind many of the 2.1 release features for Torch compile. So are you ready to see what's new? Number 1, Torch compile gets faster. So on training performance over TIM, Torchbench, and Hugging Face benchmarks, we observe on average 1.8x speedups just with simple one-line Torch compile over eager. And altogether, these 3 benchmarks include more than 180 models. And this is on top of what we reported in the beginning of the year. In fact, the numbers I pulled are from our daily, nightly performance dashboard. And so I pulled the one last week, October 11th. And here you can see we added like a really nice 30% additional geo-mean speedups over training performance. And we report inference performance for the first time in this conference. And on average, we achieve about 2x speedups, geo-mean speedups over 180 models over eager. So actually, these performance came from optimizations across the entire PT2 stack. So we significantly improved the capability of Torch Dynamo so that we can have larger compilation units, less graph breaks, and also less overhead when there is graph breaks. At inductor level, we added tons of new optimizations and tuned the parameters and heuristics. We also benefited from our downstream code generator community in terms of support for new hardware and also better code generation. In fact, among the three of them, reducing graph breaks has the biggest first-order impact throughout the entire stack, so much so that we actually work with our customers or teach them to reduce graph breaks in their user code. So that's about the speed part. The second improvement of Torch Compile is it's more deployable. We actually made major expansion of deployment scenarios in the 2.1 release for Torch Compile. That includes expanding from training to inference, from eager mode deployment to export deployment, from server to edge devices. So each one of the expansion is so significant that they deserve a talk of their own, and you'll learn more about them in the subsequent segments of this keynote. So here, right now, I actually want to highlight one not so obvious expansion of deployability. And we actually observed and experienced that when we try to test Torch Compile in production settings. It's called composability. So for any production model, we noticed that you actually need many, many advanced PyTorch features. They are non-negotiable. You cannot say, oh, it doesn't work with Torch Compile, drop it. For example, when, especially in training setting, parallelization distributed is absolutely necessary. Memory optimization is especially important because you don't want to reduce your batch size because you use Torch Compile. Customization, advanced core features like higher order ops, hooks, tensor subclasses, dynamism in the model code like dynamic shape and control flow, and other optimizations that people like to deploy in their environment like Codograph and Megatron. So not only does Torch Compile have to compose with each individual of them, they have to all work together. So we are proud to say that in the 2.1 release, we have significantly improved the composability of Torch Compile with these very advanced features. So I don't expect you to read all of those, or maybe you can take a photo of that. But these are the list of composing features that we have added to 2.1 or in the progress prototyping. Some of them are really tough to get it right, like dynamic shape, like distributed. So we have to go back to the drawing board and every time come up with new innovations. So if you're interested, actually, Edward Young has a talk on the latest on dynamic shape, and Will Constable will talk about our current thinking of Torch Compile for distributed. So to recap, PyTorch 2.1, Torch Compile, we did see a lot of validation in terms of healthy adoption signals across the different demographics that we care about. We continue to improve out-of-the-box performance for Torch Compile. You might wonder, like, what about LLM, Gen AI, Llama, right? So actually, we have a dedicated talk this afternoon from Christian and Horace on how we apply Torch Compile combined with other PyTorch native techniques to speed up LLM inference. So if you're interested, go to that talk. And we significantly improved the deployability of Torch Compile in terms of deployment scenario, in terms of number of hardware backends, and in terms of composability. But if you ask me, what is the day and night difference between last PyTorch conference and this one? I would say production. So by bringing TorchOut compile to complex production environments, this fueled a lot of the innovations that you see in the 2.1 release. As Jason Ansel commented a couple of days ago, he said that, wow, we're still in the fun part of a compiler project. So if you're interested, check out the other talks in the conference, and you'll be amazed by what we're delivering this time. With that, I'm going to pass the mic to Mario. He's going to talk about bringing TorchOut compile to yet another new places.
Hi everyone, I'm Mario Lezcano. I'm a principal software engineer at Quantsite, and I'm the tech lead of the PyTorch co-development team within Quantsite. At Quantsite, we deeply care about open source. It is for that reason that we have many of the maintainers for many Python data libraries working with us. We have also been working with Meta for the last 4 years in the development of PyTorch core. In particular, during this time, we have helped them make sure that PyTorch aligns with the rest of the Python data ecosystem, and that the Python data ecosystem can benefit from the developments within PyTorch core. Today, I'm going to present to you 2 things that are going to be released within PyTorch 2.1, and also one other thing that has already been merged in SciPy and scikit-learn that will help cement this interaction between PyTorch and the rest of the Python data ecosystem. The first feature is that Torch compile now natively understands NumPy code. So here we have a very simple example of a NumPy function. Disregard for now the Torch compile. And this NumPy function accepts 2 ND arrays and computes the sine of the first one and the cosine of the second one, puts that onto auxiliary arrays, then adds them together and returns the result. Executing this on NumPy needs to create 2 different arrays. This is not great, as this is just an artifact of NumPy executing things eagerly, same as PyTorch eager does. Just by tagging this function with Torch compile, the function will stay the same, the semantics will stay the same. It's still a function that accepts NumPy arrays and returns NumPy arrays, but Torch compile is able to understand the NumPy arrays as if they were tensors and transform all the functions into PyTorch functions and then generate very efficient C++ code, as you see on the right. All this is done automatically for you. You don't have to do anything but to tag the function with Torch compile. In this simple example, we get about a 2x speedup just by writing this one line. If only getting speedups always were this easy. Torch compile, the natively understanding of Torch compile is very important here, because this means that this feature leverages all the other features within Torch compile, all the ones that you are going to hear about today. In particular, if you have a large code base from NumPy code, you can tag it with Torch compile, and Torch compile will try to trace through it. And if it finds some construction that it doesn't understand, imagine that you're using an ND array of strings, there's no way that we are going to be able to trace through that. In those cases, Torch compile kindly asks NumPy to execute that part, and then picks up afterwards and continues compiling the rest of the code. So the very simple example that we saw before actually generalizes to much more complex code bases, which is very nice. There is also a seamless interaction between PyTorch tensors and NumPy tensors. People have already been using for a very long time PyTorch for production code, but in between, they may call .numpy to transform the tensor into an ND array, perform a few computations with the ND arrays, and then call from NumPy or as tensor to go back to PyTorch. Torch compile understands all these constructions natively. So internally, it represents ND array as tensors, and calling tensor.numpy does nothing but to tag this tensor with NumPy semantics. Then when you call as tensor or from NumPy, it just removes these tags and continues tracing with the tensor that I had underneath. All this, as the same as with the rest of Torch compile, was implemented in Python for easy hackability. So if you want to have a look at the implementation that we have of NumPy in terms of PyTorch, you can have a look at torch/_numpy within the main PyTorch code base. Everything's written in Python, so everything's very easy to play with. Here we have a much more non-trivial example where we have the main iteration loop from a k-means algorithm. Here we have a blob of points and some means, and we just compute the distances between the points and the means, and we select the minimum distances. So in this example, we see that on the left we are executing it on NumPy, and on the right we just add torch compile. Just by adding torch compile, again, the semantics of the function do not change. Like it still is a NumPy to NumPy function. But torch compile is able to compile into just one for loop, similar to what we saw in the first example. And here we get, and also it manages to execute it in multiple cores, something that NumPy doesn't do. So the fusion and the execution on multiple cores gives us here a staggering 57x speed up against the regular NumPy code. Again, doing nothing, but just tagging it with torch compile. Even cooler is that you can natively run your NumPy code now in CUDA, just by running it under torch device equals CUDA. When you do this, you execute the compile function under this context manager, and torch compile will automatically move the ND arrays onto CUDA, will execute the whole thing in CUDA, and then bring the ND arrays back to CPU and return an ND array. Again, everything is executed on CUDA, but the semantics stay the same. Like still function from ND arrays onto ND arrays, but underneath executes in CUDA. Of course, this is not great if you are going to be executing the function over and over and over in a for loop, or you just want to execute it many times because you don't want to be moving things from CPU and CUDA and then moving them back. That is not great. But NumPy doesn't have the concept of a device equals CUDA. So what you can do is you can write a tiny wrapper around this function and basically make a new function that accepts CUDA tensors, tag them with the NumPy tag, just calling x.numpy or means.numpy here in this example, trace through the whole NumPy stuff, and then removing the tag using from NumPy. There's no copies. There's no all this is traced into CUDA code, and the generated code just you end up having you end up converting a NumPy function into a CUDA PyTorch function that is compiled. With this example, you get the 200x speed up against regular NumPy, which is very cool. The second feature that I want to tell you about is not in PyTorch core. It's actually in SciPy and scikit-learn core. Two developers from Quantsite that are long-time maintainers from SciPy and scikit-learn implemented the POC in these two libraries where they implemented some modules and some algorithms within scikit-learn using the Python Array API. The Python Array API is a subset of a NumPy API that libraries like PyTorch know how to implement. When you implement functions using this subset of the NumPy API, these functions then can dispatch tensors onto that path, and in practice, they basically know how to process tensors and be executed with tensors. Here we have an example of a rather non-trivial scikit-learn algorithm, the linear discriminant analysis, that was implemented with this feature. And now it accepts CPU tensors from PyTorch, and that already gives us a reasonable speedup. But when we execute it on CUDA, we get huge speedups just by using PyTorch tensors rather than NumPy ND arrays. Consider contributing to these libraries to help expanding the support of PyTorch tensors within the Python ecosystem. The thing that all this is implemented in Python, so it's not particularly difficult to help contributing this into these libraries. And now I leave you with Will Constable, who will talk to you about distributed in PyTorch 2.1. Thank you.
Thanks, Mario. Hi, everybody. My name is Will, and I'm a software engineer at Meta working on PyTorch Distributed. So going back to last year's PyTorch conference, we announced PyTorch 2 and the headline feature with Torch Dynamo and Torch Inductor. Really impressive speedups on single GPU models, but also on distributed models using DDP and FSDP. But we weren't actually able to compile the distributed parts of these models. Instead, we leaned heavily on the graph breaks, which Peng mentioned earlier, as one of the strengths of the compiler, being able to compile the parts of the model that it could extract and capture and get speedups from, but then falling back to running native Python for the other parts. But we really want to be able to compile the distributed parts too, so we can use the compiler to optimize them. So today I'm going to talk about how we enable this. But first, why is it hard to compile distributed? So to start things off, we actually couldn't even represent the communication operators in the graph. The C10D communication library uses things like work objects and things that aren't tensors, and generally wasn't representable in FX. But without being able to put communications in the graph, what can we do? So the naive thing, if you look at this picture here on the top right, if we compile all of the forward and backward of a model, we'd have to run the communications outside. And if all the communications run outside of the graph, we aren't able to overlap them. And that kills the performance for DDP. The whole purpose of DDP is to overlap communications and computation. So we thought, what could we do about this? And one thing we could do is we could actually break the graph into smaller pieces. So we could put communications in between chunks of graph, and we could still compile parts of the graph that would contain pretty big fusion regions, and we can get the speedups we would hope for. And this actually worked pretty well. So we found that with a lot of models, we could get great speedups this way. But sometimes graph breaks add a lot of overhead. So we want to be able to remove graph breaks. And we don't want to be beholden to using graph breaks as the only way to support distributed. So we want to be able to compile distributed libraries, not just run them outside the graph. So how can we do that? Well, the first thing we have to do is we have to actually be able to support capturing and representing the collective communications. And so we enabled that by adding functional collectives to the compiler. And now we have a way to represent communication operations in a way that they're able to be captured by the Dynamo front end. We can represent them through and transform them with the compiler. And they can run in eager, allowing overlap in eager PyTorch, but they can also run, they look like they're functional, and they can be lowered to inductor code that then overlaps again. So we solved this problem. But it still isn't very easy to capture all of the distributed library code because they use a lot of capabilities of PyTorch, more advanced extension points, and things that Dynamo's front end didn't support yet. So it would be tempting to just take note of the fact that most of the complexity in the distributed code base comes from trying to support and optimize an eager PyTorch, where we don't have a compiler, and we want to do things like scheduling and grouping and reordering without a compiler. We add a lot of complexity for that. If we actually just want to compile and use the compiler to optimize, we could just rewrite all this stuff and make it simpler for the compiler. But we don't want to diverge the user experience. We don't want to have different sets of APIs for distributed compile and regular distributed. We want users to just be able to slap compile around their model and get speedups. So we need to lean on this concept of composability. We develop a bunch of different components as separate teams, and we want them to fit together nicely. And this matters also for distributed on its own, because we want to be doing things like two-dimensional and three-dimensional parallelism. We need to put together all these pieces in different ways. So to do that, we leverage things like module hooks and autograd hooks and tensor subclasses, concepts that are well-defined in core infrastructure. And by doing that, we can make our pieces fit together better, but we can also give the compiler a reduced surface area that it needs to support in order to enable compiling all these things. And so as Peng mentioned earlier, we've got projects that either landed or in prototype phase for covering all these areas. We've got support for module hooks. We have a compiled backward that's almost ready. We have support for tensor subclasses that's partially landed now, and I think pretty close to being landed and ready. And once we have all of that, we'll be able to compile all these distributed library components. And so once we've got a graph with distributed communication operations inside it, there's a lot of stuff we can do. Starting off with solving some user pain points. With DDP, users have to tune their bucket size. And with FSDP, users wrap parts of their model in FSDP subunits. And both of these are kind of manual operations that you can either use the default and not get great perf, or you can spend some time optimizing it. And we wanted to just lean on the compiler for this. There's also cases where we've got a graph full of operations, and we've got communications and computations, and sometimes they don't all depend on each other linearly. So there's multiple possible schedules. And we want to be able to reorder and prioritize scheduling communications so that we keep comms and compute overlapping. So one really cool example of this is the tensor parallel pattern that we see in large language models. So we start off with a row-wise sharded input and a column-wise sharded weight, and we do a matrix multiply. But before we can do the matrix multiply, we have to do an all-gather. And unlike in data parallel, where we can overlap these all-gathers with compute, this all-gather seems to be fully exposed, and we have to just wait for it to finish before we can start doing compute. But it's actually possible to completely hide this communication if you take this matrix multiply and break it up into smaller pieces. You can actually take the chunks of your input tensor and send them around in a ring of your peers and overlap these exchanges of input data with doing smaller chunks of matrix multiply. And by doing that, you can save a bunch of time and overlap the communications. So users could do this by changing their model code, but it's pretty complex, and we don't want them to have to do that. When we have a compiler that can actually just recognize this pattern and implement the optimization automatically. So in summary, we're really excited about being able to compile distributed because we can start to experiment with all kinds of different optimizations for the compiler. So enough about distributed and training. Now I want to hear about inference, so I'm going to call Mark up to the stage and talk about that. Thanks.
Hey everyone, I'm Mark, and I'm here to tell you about our inference story. So last year we released Torch Compile, and it was like one of the very first training compilers on the market. So a lot of people have been excited about what we have in store for inference. So I'm here to announce that we have our new inference compiler, and that is also Torch Compile. The great thing about this is that because training is a superset of inference, we don't need to rebuild a whole set of new infrastructure. So what am I really saying here? What I'm also implying is that you're not just using Torch Compile, but also use Python in production. So hardware is expensive, even if you can find it. So a tale as old as time is you have a program that's slow, and you might think hey, I want to rewrite this in C++ and make it much faster and cheaper. So the goal of this talk is to really convince you is instead of saying I should write that in C++, you should just keep that in Python. That's really my goal for the next couple of minutes. So Python's great because it's easy to write, but Python maybe is not so great because it's a bit slow. And one way you might convince yourself that it's slow is maybe running a benchmark like this. So this is a naive merge sort implementation that I wrote in Python versus C++. And you can notice the C++ version, this is a log scale. It's about an order of magnitude faster, 10x faster. Well, 10x is great. We also want our PyTorch programs to run 10x greater. So how does this work there? Well, the first thing that you might need to come to grips with is well, in 2022, more than half of PyTorch was written in C++. Today, or at least in September 29, more than half of PyTorch was written in Python. Yet PyTorch got faster. So what's really going on here? So this is a micro benchmark I have, and I think micro benchmarks are great because computers are complicated. This is a good way of understanding them. So in this program, I'm instantiating a 10K tensor and just adding 1 to it. And then measuring how long this takes in Python versus C++. In Python, we get about 6 microseconds, not bad. C++, around 5, 20% faster. No, great, 20% fast, I'll take it. Let's do a bit of a more complicated program. Instead of adding 1 once, we add 1 twice. So we have these 2 add 1 statements. So now the difference, well, the runtime for both programs about doubled. Yet the performance, like the difference between the C++ and Python implementation went down. Like now C++ is only about 19% faster. And you can make this number go further down the more complex your program gets. So I deliberately picked like a very simple program here. So how do you actually make a program like this faster? So instead of adding 1 twice, you add 2 once. So you essentially fuse both operations, and now you get like a 2x speedup. The C++ version is still like a bit faster, but let's say this was the original program with your goal of making it faster. You have these 2 add-1 statements. On one hand, you could rewrite your stack in C++, get 22% faster, or you could just like fuse those 2 ops and get a 2x speedup. And when we talk about Torch compile is essentially a fusion compiler. What it will do is like look at like these kinds of optimizations you make in your programs and make them faster. And this is really the optimization and the real bottleneck that matters on a lot of like real code. So you might be thinking, well, you know, what's up with Torch script, right? And well, where did the speedups from Torch script come from? Like C++? You know, no, it was actually because it had fusions. But the problem is those fusions were really hard to write because we had to write them in C++. So this is sort of our promise. And this is how I think about the user experience of JIT versus compile. JIT was a step function. You had to spend a whole bunch of effort to get like the first speed up boost. Whereas with Torch compile, you should just like run it, and it should just be faster than eager if you make no changes to your program. And the more effort you're willing to spend by removing graph breaks, the faster your program can get. But it doesn't remove effort. It just defers it over time. So you're not bottlenecked by shipping something to production by having to remove like all graph breaks. And the performance speedups can be quite substantial. Like they can be like basically three-digit speedups. So like we're not talking small numbers. So some people you know, hate removing graph breaks. So I've met some people that enjoy them. But there's 2 tools that I really, really highly recommend that you check out to remove them from your programs. The first one is like an explained backend added by Michael Voss. And the other one is like our logging mode added by Michael Lassos. The general heuristic that you'll find very helpful in removing graph breaks from your model is writing your code in pure PyTorch. So for example, you know, don't use like clever list comprehensions, use torch stack. Don't use like copy.copy, use like torch.clone, use torch where. So like try to have as much of your program be in pure PyTorch. So great, you went through all of this effort, was it worth it? Well, in the case of like Patrick von Platen, who's like the Hugging Face diffusers maintainer, after removing all graph breaks from their models and using SDPA, they were able to get like 100% speedups on their stable diffusion models. For PyG, Matthias Fey used like Torch compile recently, and after removing all of their graph breaks, like their speedups were even more substantial, 300% speedups. So again, we want like 3-digit. Like 3-digit feels good. All right. So you might also think, well, the time it takes to run a single inference is one part of the story, but the other is cold starts. So again, let's just look at some micro benchmarks again. So this is actually like, I took a model that a lot of people care about these days, like Llama 7B, and I ran a couple of micro benchmarks. Compiling it with Torch compile takes about 60 seconds. Just torch.loading it naively, another 60 seconds. Running an inference, this is like very big O-ish, but you know, let's say about 3 seconds. Importing Torch, another 3 seconds. And this is a log scale, so now the numbers go down quite a bit. Like initializing the CUDA context, about 70 milliseconds. Let's say you're deploying this in a web server, about 50 milliseconds, maybe less. And then launching a Python process, about like 3 milliseconds. So for the bottom 3, we don't have like all that much like control over them. So I'm just gonna show you how you can optimize like the top 4. So the first one is like Torch compile is a JIT compiler. And JIT compilers have a startup overhead. And the way to reduce like startup overheads is you cache things. So there's a whole bunch of caches, but like one particularly interesting one was contributed by Ani Viros at IBM, and recently merged by Sam Larson at Meta, which is the FX code cache. And this one like brought up the warm compilation times from 60 seconds to about like 40 seconds. Another one is you might think like, hey, like I want to like load a model, and this is like a pattern that I found like in the wild in the LibGPT code base, where by using meta device initialization and like mmap contributed by like Michaela Gawarski, you can like load Llama 10 times faster. The other thing, an optimization I wish we could turn on by default, but we can't because it has like some memory overhead that Elias Elson is working really hard on reducing, is reduce overhead, which will enable CUDA graphs. Like this with Fusion will give you like most of the speedups that are important. And finally, like importing Torch can be made like much faster with lazy imports. So this is like a 10-line PR added by like Nikita Shulga in Torch init, where you only basically import like what you really need, which makes sense as Torch grows as a library. So whether like you're a researcher, whether you're like a larger company, you care about like your model iteration cycles, Python is great. But if you also care about speedups, Python is also great. There's just like more work you need to do with the cold start times. And this isn't even in the short term. In the long term, there's like some long known bottlenecks in the Python community, like multi-threaded inference and data loading, which will go away thanks to the No-GIL project in the next couple of years. And we're very thankful that Sam Gross is actually on the PyTorch team to drive a lot of these big changes forward. That said, I understand like for a lot of people, like there's like some constraints for eager-based deployments. And we also have a solution for you. And I'd love to welcome Yanan on stage to tell you all about it. Thank you.
Hello, everyone, and thank you, Mark. I'm Yanan from PyTorch team and Meta. And today I'm going to talk about the new PyTorch export path. So Mark asked a great question. What kind of scenarios do we have that we cannot deploy Python? There are indeed a few. First, there are scenarios where we cannot have a Python runtime. Let's say if you think about a mobile or edge device, where additional Python runtime means additional overhead in binary size, power consumption, and memory footprint. That's generally not allowed in a phone app. Or there are cases where you have a service that's extremely performance sensitive, where every millisecond must be accounted for, and every millisecond you can save means high ROI for you. Think about self-driving cars, where unexpected latency could literally mean life and death situation. Or if you want to interop PyTorch with a different system, and a lot of systems in the ML world requires a graph as input, and they want to take over the control of the execution of the entire program. These examples are, say, you have a specialized backend like TensorRT, and they all require a solution. And we propose export as the solution. And export is basically translating Python code to a full graph. If you look at the picture on the left, that's how a PyTorch model is generally represented. It's a bunch of tensor computations hidden within Python code. An export's job is to distill the fundamental tensor computations from the Python code into something pure, cleaner, into data. And that's not specific to any programming language or runtime. And this full graph concept is fairly powerful. It does come with a cost. Compared to Torch compile, it may require to rewrite some of the code, because some Python code cannot be reliably translated into a static graph. But it also has a few major upsides. First of all, you won't have any Python overhead if it's gone. And you have lower framework overhead because we can eliminate that during the export process. And because you now have a full view of the program, you can unlock all the optimization potentials so that you can optimize your performance. And last, which is not shown here, but because now you have a full graph representing the entire program, you can naturally interop with all the systems that need a graph. Because by nature, they're now speaking the same language now. And we call this full graph generated by Torch export, export IR. We aim to have export IR enable you to analyze your program, transform it. You can save it into a file, load it up in a different environment for execution. And if you want, you can further translate it into a different compiler for further optimization. And to export a program is fairly simple. You first need to construct an module like usual. Then you train it in Eager. Then you prepare a set of example inputs that should represent what normal input would look like that your program is designed to handle. Then you just call this one line, says export, with example inputs in there. What happens underneath is that export will trace your program and record operations produced by PyTorch. So you say, it's just another tracer, simple. But why do we need another tracer when we have quite a few in PyTorch? Because this tracer is different, it's safer. If you think about normal tracing approach, that's usually you have an operation recorder on the side, watching what PyTorch is doing, and write down every single operation being run. Well, that's simple and works in a lot of cases, But unfortunately, it has a fatal pitfall. That is, there's a soundness problem. During execution of a PyTorch program, PyTorch makes a lot of branching decisions, which kernel to invoke, which code path to run, and these assumptions are usually hidden from the user. So the user will not get a chance to look at the assumptions or examine them. So when they deploy the model, there can usually be a nasty surprise for them when they input a different type of input to the program. That's why we propose sound tracing, which is really a change of perspective. Instead of saying we can safely translate just the PyTorch model into a graph, we say we need more. And this additional thing is we want to leverage user insight to tell us what kind of inputs are really valid, and we're going to do diligence to check whether these insights are enough to ensure that the program is justified. So in this case, users have to say that tensor shape is greater than 4 for us to produce a graph. Otherwise, it will create an error. And in practice, we find that only tensor shapes information are useful in determining whether a program can be translated or not. For example, in that case, it's about the tensor of the input. And this, of course, is only needed for models that have dynamic shapes. For static shapes, everything is handled for you automatically for you. So when user provides this dynamic shape information, Torch Export is going to check all dynamic shape information against all the assumptions produced during execution. And only when all these checks pass, Export will give you an export graph. Otherwise, it'll error out with explicit suggestions on what additional information should be added in order for it to succeed. And when export succeeds, it's going to produce export IR, which is a linear sequence of operations in A10 or custom ops connected by tensors that represent semantics of the original program. With export IR, it's housed in a TorchFX graph, so you can use standard TorchFX tools to perform transformation and analysis to it. We also provide a canonical serialization format where you can save the export IR into a file and load it back to get the same IR. Export IR can be used as an extension point where you can export the program once and lower it to many different backends. With collaboration from our partners, we have already supported a few backends, ranging from edge devices, general purpose computing like GPUs, or specialized hardware. And this is what our partners have to say about Torch Export. I'm happy to see that Torch Export is providing value for them, and I'm confident many of you will find it useful too. So last year, we unveiled PyTorch 2 with Torch Inductor backend with amazing performance by JIT compiling PyTorch program. And this year, with Torch Export, we unlock a new way of tapping into the power of a Torch Inductor that is in a ahead-of-time fashion. And we're happy to announce that we can achieve 98% model coverage for Hugging Face and Team benchmark sets and delivering 2 times speed up for the same bench. You can try out Torch Export today by installing PyTorch in the nightly channel to get the latest features. And we have prepared a tutorial for you to get a step-by-step guide into learning how to use it. And next, I'll welcome Mergen to dive into ExecuTorch, which is a cutting-edge edge deployment platform that harnesses the power of Torch Export.
Thank you. Hello, everyone. My name is Mergen Nachin. I'm a software engineer at Meta working on PyTorch. Today, I am thrilled to announce ExecuTorch, our all-new end-to-end solution for deploying AI for on-device, specifically for mobile and edge devices. So today, AI models are extending beyond server to edge devices such as mobile, AR, VR, MR headsets, wearables, embedded systems, and microcontrollers. And on-device use cases enables many new real-world applications because of such benefits such as low latency, enhanced privacy, and being able to operate in offline or remote environments. However, designing for edge device presents many challenges. Usually the edge devices are quite restricted in terms of battery, restricted in terms of thermal requirements, and as well as restricted in terms of memory. And moreover, the current landscape is quite fragmented, and there's a wide variety of hardwares and tool chains available. So as of today, let's take a look into specifically how you do on-device AI. You take 4 PyTorch models, right? You take a PyTorch NN module, and then you convert it to other formats before deploying into these embedded devices. And it actually presents many challenges. There are opaque and conversion tools for different devices. There's no consistent experience for debugging and profiling. There could be compatibility failures when you're converting one model to another. And lastly, there is an authoring and deployment mismatch, semantics mismatch, which will result in inaccuracies of the model. So we basically designed this new solution called ExecuTorch from the ground up to rethink fundamentals and tailor specifically for edge devices. So I'll talk a very high-level overview of this. So we have 2 components. One is the ahead-of-time components, and then the runtime component. In the ahead-of-time components, we start with PyTorch NN module, torch.nl module. You convert it to semantically equivalent exporter graph. You're using the same API that Yanan just talked, torch.export. And then once you have the graph, we provide entry points for further transformations and compilations to target to a specific device. And then it gets converted to ExecuTorch program, which is, and then during the runtime, the ExecuTorch runtime program gets loaded to the runtime, to the edge device, and be able to execute inference very, very efficiently. Throughout this workflow, I would like to say this, developers use the same consistent API and SDK for that with debugging and profiling support without, so that, okay. So they actually go through the same experience. And as a result of this, developers don't need to go to outside of PyTorch ecosystem to develop, to deploy on-device AI. So I would like to talk about 3 benefits and 3 focuses. So the first one is portability. ExecuTorch is able to run on both mobile and embedded devices. And secondly, productivity. Same flow can be used both for mobile and embedded devices. And one of the design choices we did is that we focused on modularity and composability. And as a result, developers can pick and choose different optimization techniques to tailor towards their specific use cases. And lastly, as I mentioned in my previous slide, we have native first-class SDK support for debugging and profiling. And last but not least, we provide good performance. Namely, our runtime is very nimble and can run very well on the embedded devices. But more on top of that, you can delegate to other accelerators provided by XNMPack or third-party delegates. I'm happy to announce that as of today, ExecuTorch is powering AI inference on Meta devices. It has shipped to the smart glasses that was just announced, the Ray-Ban Meta smart glasses, and it's also coming to the Quest 3 VR headset soon. So I mentioned this the last bit because I would like to emphasize that ExecuTorch was validated and vetted by an actual real world engineering problems. So in my previous slide, I told about that. In my first slide, I told about that the on-device ecosystem is very fragmented, right? So we, as a community, need to work, as an industry and the community need to work together and collaboratively to actually be very successful in this ecosystem. So I'm very happy to announce that we have 3 partners that we work very closely, Apple, ARM, and Qualcomm. And I see some of the folks here in this podium here, in this venue here. And what it means is that from a developer point of view, developers can deploy PyTorch models on device and take full advantage of the hardware capabilities provided by these partners. So this is only possible because of the design decisions we've made, and specifically export and export IR that Yanan talked previously, Core 18 operator sets, and as well as well-defined entry points for both compilers, delegations, and quantization. So it is available right now. This is, we just had our first release, 0.1 version. github.com/pytorch/executorch, you can download. And what you can do with this is that you can download the code, and we provide 10 common examples with wide variety of architectures. We also have example tutorials, including deployment to Android, iOS, ARM embedded systems, and as well as extensive DSP. But more importantly, you can actually try your own model onto your own device and see how it works. And we have 3 technical sessions throughout in the morning. And we also have a booth where we are demoing the actual on-device deployment there. All right, so the future. So today, we are, as I said, we are open sourcing ExecuTorch. And it's still very early, but we are open sourcing ExecuTorch because we want to get feedback from the community and embrace the community. And throughout the next few months, we're going to harden it. We're going to focus on enriching the delegates, enriching the SDK. And in next year, we also plan to have much better, tighter community interaction with, let's say, libraries and frameworks, and also improve the performance even further. So ExecuTorch is, we as Meta will be focusing on improving and investing in ExecuTorch as the edge solution. But I would like to actually step back and say ExecuTorch is under an umbrella, PyTorch org. PyTorch orgs under an edge umbrella. You know, trying to, this will be one of the many initiatives we're going to expand in terms of in the edge space. And thank you very much. My name is Mergen, and I would like to hand it back to Joe now. All right. Yeah.
Great job. Okay, we're going to head into a coffee break. But first off, I'd like to thank all the speakers in the morning. Great talks, everyone. Give everyone a round of applause. So 2 things. Go to the atrium, hang out with the sponsors. There's some booths set up out there. There's coffee. And then the breakout sessions actually start at 10:45. So time to network, time to chill, and we'll see you all at 10:45.